Okay, so good morning to you all. Hope everybody has joined.
Good morning, sir.
Yeah, good morning. Okay, so till yesterday, so we were discussing about the slope stability of an infinite slope. So we try to understand a little bit about how the slope can fail and how to determine the stability factor with respect to cohesion, with respect to angle of internal friction, so on and so forth. So today, and let us talk about the another method, that is Kalman's method of analyzing the slopes. Based on the similar assumption, that is the surface of the failure planar. That means it's like an edge failure. So in yesterday's case where the slope is infinite, so we have the plane surface, so it is like an horizontal line, so starting somewhere and ending somewhere, so where there was no starting and ending the points. While today, so we will discuss about the Kalman's method. This is one of the very first person who dealt with the slope stability analysis. So his assumption is based on the surface is a planar. So as you can see in this picture, so there is a wedge called as a ABC. The height of the wedge is h, and the angle made by the slope is beta, and angle made by the failure plane is theta. So angle made by the slope is beta, and angle made by failure plane is beta. Sorry, yeah, failure plane is theta. So when it is a wedge failure, then this forms some kind of a triangular surface. So this forms some kind of a triangle. So this is called as a wedge. So it is assumed that so this entire mass of wedge slides down and causing the failure of the slope. So this is based on the assumption. Now herein we need to understand so where the shear strength develops and where the shear stress develops. So here only the wedge ABC, the mass of this soil mass only can induce some amount of the shear stress within the soil mass. So therefore we can term W as the weight of the wedge ABC, weight of the wedge ABC, and the shear strength is developing opposite to the moment of the wedge ABC. So therefore the reaction R designates the shear strength development. But of course the shear strength equation is this one. So tau is equal to C plus sigma tan pi dash. So sigma tan pi, whatever it is. So now when there was a wedge, so that is axial stress, then this causes the development of normal stress and shear stress all along the failure plane. So consequently the normal stress is represented in the form of a weight and with some other component, and shear stress we directly take into account the which is causing the instability within the slope. Instability within the slope. As you can see here, so the W is in vertical direction and the reaction is also direction but in opposite to W. So we can resolve W into two components, normal component and the tangential component. The planar plane surface, the tangential component perfectly lies along the plane failure plane, and normal component is perpendicular to the line AC. So line AC. So the very first step is first of all you need to determine, so like the previous class, the weight of the wedge ABC. So this is a triangle. So this is how one can able to determine the weight of the wedge of base into height, and the volume is per unit meter. So this is density multiplied by height multiplied by the base width of base into height. This is a triangle, simple triangle. So height is known, that is a capital H, gamma is the density of the soil sample, and in the perpendicular direction to this screen there is a 1 meter, that is per unit length. Then BC is the base width of the triangle. So base width of the triangle. So the BC can be determined simply so based on the triangular geometry principle. So the BC will become h cot theta minus h cot beta. So h is h and gamma. And if you simply simplify the cot into sine, so then this is the form that you normally get it. So of gamma h square into sine beta minus theta by sine beta into sine theta. So this follows the principle of sine of a plus b or sine of a minus b or tan of a plus b or tan of a minus b. So if you further simplify, so you will get this kind of an expression of gamma h square into sine beta minus theta by sine beta plus theta. So this is how one can able to determine the weight. So then the next step is to determine the normal component and the tangential component. So if we resolve the forces in normal direction and tangential direction of the W, so NA is nothing but W cos theta. NA is nothing but this is theta. So this is theta. So this is NA is W cos theta and TA is W sin theta. So TA is W sin theta. So if you substitute everything, then half gamma h square W is half gamma h square into sin beta minus theta by sin beta into sin theta and multiply with the sin theta. Similarly, so if you resolve W into tangential component, that is W sin theta, then substitute the value of W, so then this will become so tangential component. So then convert these forces into the stresses. So normal stress is divided by the area. So that is AC. So this is the all along the plane of AC, the normal stress is developing. So therefore we will take the and multiplied by 1 unit length. So that is 1 meter. So NA by HY sin theta. Suppose if you determine the length of the AC, this will become H by sin theta. The length, the chord length of AC is H by sin theta. Then if you substitute the NA, so which has been already so derived here. So if you substitute everything into here, then sigma dash will become half gamma h into sin beta minus theta by sin beta into sin theta multiplied by so sin theta cos theta into sin theta. So h will get 1 h will get cancelled out. So in NA term, so therefore this will become half gamma h. Similarly, try to determine the average shear stress, that is shear force divided by area. Shear force divided by area. So A is the length of the AC is h by sin theta. So we know the TA. So we already derived the equation for TA. Simply substitute here. Then try to simplify and you will get half gamma h into sin beta minus theta by sin beta into sin theta into sin square. So this is sin theta into cos theta, that is sigma dash, and sin square theta, that is tau. And this is the equation for total shear strength or effective shear stress. So the average effective resistance resist to shear stress. That is this is a cohesion component plus sigma dash is known half gamma h into beta minus theta into cos theta tan theta. So cos theta sin theta, and this is tan theta dash. Substitute the value of normal stress in this shear stress equation. So in this shear stress equation. So similarly, when you are determining the factor of safety, the shear stress must be equal to the shear strength of the soil sample. The shear stress and shear strength. So that's how we define the factor of safety. Shear strength should be more than the shear stress of the soil sample. So we have derived equation for the shear stress. So substitute here, then substitute in the shear strength equation. So this is the shear stress and this is shear strength, or maybe reverse. Oh, this is okay. This is shear strength, and you try to rearrange all the terminology. So into H, this is what we have done in the previous in yesterday's class also related to the infinite slope. So CD, and try to differentiate with respect to 0 in order to derive So our requirement, what is the critical angle at which the slope can fail? So this is critical angle. So if you differentiate the equation and further simplify all these analytical equations, so then what you will get is theta critical, that is angle made by the failure plane, will become beta plus pi dash d by 2. This is average of the slope angle plus friction angle. So substitute theta is equal to theta critical, so into CD dash equation. So then rearrange all the equations. Rearrange all the equations. So either you can determine using the Kalman's method the factor of safety, or this equation is more prevalently used to determine the critical height of the slope. Critical height of the slope. So here in this equation, when you have rearranged C dash by gamma h, and this is also again called as a stability number. All C dash by gamma h, wherever it is coming in, whichever the theory it is. So it is called as a stability number. So Taylor has defined C dash by gamma h as some kind of a number, that is n-dimensional coefficient, n-dimensional parameter. C dash by gamma h is stability number. So m is equal to 1 minus cos into beta minus pi dash by 4 sin beta into cos theta. So there is an inherent advantage of converting C dash by gamma h for a particular value of C dash by gamma h, and by varying the slope angle beta and theta, one can able to develop several kind of a predefined charts. So we don't need to every time calculate what would be the value of the critical height or something. If there are some predefined chart, so for a given friction angle and for a given slope, so one can able to determine what would be the critical height, or so try to pick up the value of the C dash by gamma h directly. So for a given slope and for a given friction angle, it is as simple as possible. So we can define a bunch of graphs between beta and pi dash and correlate everything with C dash by gamma h. So when beta is known, when angle of internal friction is known, so from the predefined chart, pick up the value of C dash by gamma h and try to determine the critical height of the slope. That is the beauty of the stability number. So the maximum height of the slope can be determined by using this equation. So h critical is equal to 4 C dash by gamma. Of the equation is remain as it is. So the maximum height of the slope by substituting CD dash is equal to C dash and pi d dash is equal to pi. So in case if you want to determine the factor of safety here, again we can go for two things. Try to substitute CD is equals to C dash by the factor of safety with respect overall, or so tan pi dash is equals to tan pi dash, or tan pi d is nothing but so tan pi dash m by so factor of safety. So if you want to determine the factor of safety, you can keep on substituting these C dash is equal to C by factor of safety and tan pi d is equal to tan pi in this equation. Or if you don't want the factor of safety, if you are assuming that the factor of safety is approximately 1, where it is on the verge of stable condition, then one can able to determine the minimum height of the slope required. Okay, so the same equation can be converted into determining the factor of safety for a known height of the slope, or if you are assuming that the factor of safety is unity, then what would be the critical height of the slope as per the Kalman's method. So here I have taken a very simple example. So whatever we have discussed in the previous slide, just try to understand so by this simple problem. So determine by Kalman's method the critical height of an embankment having a slope angle of 40 degree and the constructed soil having C dash of 630 psf. So this is not SI units, pi dash is 20 degree and effective is 114 pound per cubic feet. So find the allowable height of embankment if FC is equals to Fi is equals to 1.25. So this is simple demonstration of whatever I am talking in the previous slide. So first the part A of this sum is, so determine the critical height of the embankment. When somebody says the critical height, so it inherently assumes that of safety corresponding to that critical height is 1. So anything becomes the critical when the factor of safety is 1. So assuming that the factor of safety is unity, so factor of safety is unity in this equation, then critical height equation is 4c dash by 4c dash into sine beta cos dash by gamma into 1 minus cos beta minus pi dash. So here everything has been given. C dash of the soil is 630 psf, then beta, that is slope angle, is 40 degree, then internal friction angle of the soil is 20 degree, so 20 degree. So substitute everything into this equation, then the critical height of the slope that we can get is 221 feet. 221 feet. So when the factor of safety is 1, so then we can build a slope up to a height of 221 feet. Okay. Now another question is, suppose if you want to maintain a factor of safety of 1.25, then what would be the limiting height of the slope? Limiting height of the slope. So then again, so Fc is equals to Fy is equals to 1.25. Then as we know from the previous classes, the mobilized coefficient is nothing but the final coefficient divided by the factor of safety. So 630 divided by 1.25, 504 pound per square feet. Similarly, the mobilized angle of internal friction tan pi dash m is equals to tan pi dash by f of pi. So that is, here both are same. So tan 20 divided by 1.25. So that is 0.291, pi dash is 16.23. So make sure that the mobilized cohesion and the mobilized angle of internal frictions are lesser than the cohesion and friction angle at failure. So at failure, the cohesion is 630. Therefore, the mobilized is 504. 504 is lesser than 630. So it is all right. Similarly, the friction angle at failure is 20 degree, but the mobilization is starting when the friction angle is just reaching the 16.23. So this is lesser than the 20. So our values are correct. Our values are correct. So then once C dash M and pi dash M are known, so then allowable height, so as per this equation is, so same, substitute in the above equation, then what you get is 128.7 feet. 128.7 feet. You can see hoping only half the slope. Only half the slope. So just try to imagine, when you are taking a factor of safety of 1, it is 221 feet, that much height we can go. But when the factor of safety is increased from 1 to 1.2, just increase the factor of safety by 0.25, then you need to cut down the height by almost half. Almost half. But of course, there was no relevance between the factor of safety and something. There is no direct relationship. Okay, so they can vary. Even small value of the factor of safety, so can change a significant in the embankment. Okay, so just further to enforce the understanding of this one, now when I say, let me ask a couple of questions. When I say Fc is equals to Fy is equals to 1.25, so is this 1.25 is also valid with respect to the strength? Can I say this 1.25 value is approximately equivalent to the strength?
Yes, sir.
Okay, good. So any other suggestions or any other comments?
I think no, sir.
Okay.
Excuse me, sir.
Yeah.
So what's the difference between critical height and allowable height?
Critical height means when the factor of safety is 1.
Okay, sir.
Okay. Okay. And when the factor of safety is given as 1.25, so corresponding to this factor of safety, what would be the height?
Okay, okay, so we can or else say like allowable height is the height corresponding to mobilized value, whereas
Uh,
critical is for effective.
no, there is nothing like that. There is no effective. So Here we can say that allowable height is something related to the mobilized one, but the critical height means all critical heights or the critical depths are default belong to factor of safety of 1.
Okay, sir.
So critical means above is safe, below is failing.
Okay, sir.
Okay, so just can we all do something? Now suppose instead of 1.25, so I'm giving the FC of 1. Say 3 and F5 so as 1.1. So can you try to determine the allowable height? Can anybody tell me? And make a reverse also. So for these two cases, first case 1, so case 1 where FC is 1.3 and Fi is 1.1. So try to determine the allowable height. Now just try to reverse it. So FC is 1.1 and Fi is 1.3. So what is the allowable height? So can anybody quickly calculate and tell me?
For case 1, it is 146.53.
146.53.
Yes.
Okay, so this is 146.5 feet. And case 2,
139.73.
139.
139.73.
So okay, so 139.7. Very good. So others just try to verify this one. So when you have taken the
Yes, sir.
value,
Yes,
Coming
sir.
same for me.
Same,
very
sir.
good, very good. So now let us try to make some kind of an inferences based on these 4 values. So based on these 4 values, can anybody comment on among the cohesion and the friction angle, which one is dominating or which one is most important? Is it the cohesion or is it the friction angle?
Sir, it will depend upon the nature of the soil present.
No, the same is reflected in the form of FC and Fi na? When you talk
Sir,
about
it is cohesion.
so cohesion
Uh,
is more
yes.
dominant than the friction angle.
Yes, sir. Because if we increase the factor of safety of cohesion, the height is decreasing more.
Height is increasing more or decreasing more?
In, increasing more.
Acha, so we can go for more and more height of the embankment.
Yes, sir.
Suppose if we increase the factor of safety against the friction,
The height is decreasing.
so your height is decreasing. So what does that mean? So when you are increasing the factor of safety against the cohesion, your slope is increasing. So, but when you are increasing the factor of safety against the friction, your height is decreasing. So anybody can able to understand and give me some kind of inferences. What does that mean?
Sir, when we should increase the factor of safety, the height should decrease.
Height should decrease.
Yes, because we are taking more of factor of safety, means we are taking our result to more safer side.
Okay.
So as we are taking our result to more safer side, thus we'll get less height.
That is true. But let us look at here. When you are increasing the factor of safety in case 1, but you are getting more height than the previous one. So earlier it was 1.25, but when we increased the factor of safety, then we got the more height. So as per your analogy, so for case 1, the height should be less than 128, but we are getting more than 128.
Means friction factor for friction is more dominant here, because we are decreasing F5 to 1.1 also. So the analogy will be true for F5 here, because we are decreasing. So I think more dominant will be F5.
Okay, very good. So what about the case 2? See, for a better understanding, what you should do is, suppose you keep the Fi as a constant value and keep on increasing the Fc. Keep on determining the height value. So you can develop several number of predefined graphs. Okay, and keep Fc is constant and increasing the Fi value and keep on determining the height of the slope. Then if you superimpose all these cases on a single graph, then you will understand. So up to certain height, the cohesion is dominating. For the remaining height, the friction is dominating. So it is not the solo mechanism of the cohesion or the solo mechanism of the friction. So they proportionately change their role depending upon the height. You got it? So, but at what height the friction dominates the cohesion or the cohesion dominates the height? Here we can't able to determine unless you develop several number of a spectrum of predefined graphs by keeping one parameter constant, another parameter variable, and keep on determining the height of the slope. So that is the one of the best way of understanding. So where for what height the cohesion dominates and for what height the friction dominates. So this is how you should understand the real life problems. Okay, then accordingly you should make a remedial corrections or remedial measures when you are dealing with failure of any slope. Okay, so that's all about the Kalman's method. So this is very simple method. So let us go into the analysis of the finite slopes. After infinite the slopes, after covering the infinite slopes, then let us go for the finite slope. So the finite slope is a vast portion. So I will try to take as many number of classes as possible because this is one of the important chapter for any geotechnical engineer or for say any civil engineer, especially for geotechnical and transportation engineering people. The slope stability analysis is one of the core. So if you understand carefully, so then you can understand about the construction of any road or any embankment on a soft soil, then what kind of the remedial measures or the precautionary measures one should take. And especially when you are dealing with construction of a roads on a soft soils where there is a possibility of the consolidation and where there is a possibility of the pore pressure. So all these can be understood when you understood the slope stability. Okay, so dealing with infinite slope is relatively uh, little slow, a little remote. Okay, but we always have to deal with the finite slopes. Finite slopes. Okay, so when you talk about the finite slope, you are all well aware that so they all undergo two varieties of the failure, but predominantly it is assumed as the circular in nature. Only confined to the circular, so it is circular or log spiral, circular with translational or rotational, so on and so forth. But for mathematical jugglery and for simplification of all the mathematical analysis, so most of them have assumed that the failure surface is circular in nature. Circular in nature. So these things, the modes of failure, everybody knows. When you talk about the slope or an embankment, it can fail in three ways. The slope may be confined to the slope within the slope itself, or the failure plane may be passing through the toe, or the failure plane may be passing through the base of the embankment. So predominantly the slope failure or the confinement of the slope failure within the face dominantly happens when there was a contrast in the density of the material. So that means when the compaction is inappropriate, where the above soil is compacted high and below soil is low, or vice versa, then one can able to see so the slope kind of a failure. When there is a density contrast, so then we can see this typical slope failure. But as such, there was no problem with the slope failure because here very limited area is involved. Only the small chunk of the soil can dislocate from one place to the another place, and as such there was no problem. And the remedial measures also so quite simple. But the most troublesome are the toe failure and the base failure, and especially among the between toe failure and the base failure, the base failure is the more danger. The reason being, suppose when you deal with the toe failure, the failure plane is emerging at the toe of the slope. So usually the toe of the slope is always remain confined to our particular boundary. Our particular boundary. That means the area within which you are working. But when you talk about the base failure, often it may so happen that the point at which the other end of the slope is emerging, it may be within our boundary or maybe it is the boundary of others' property. So as long as this emergence exit point is within our boundary, we don't have any problem. But just imagine, so this is emerging in others' property, then there is a huge problem. So then there is a litigations, there is a sue, so then they can put any kind of a case, so on and so forth. So this is one of the fundamental reason the base failure is attracting immense attention by the engineers. And predominantly the base failure can happen when there exists a soft soil or the compacted soil. So this is the basic reason. So when exists a soft soil beneath the embankment, then there is a possibility of the slope failing under base failure mode. Base failure mode. When I say the finite slopes, the height of the embankment is always known and the failure plane is always circular in nature. So these are the two fundamental assumptions. Then apart from this, there are other assumptions like the soil is homogeneous and so on and so forth. So there are some methods which deal with only one layer of the soil, and there are some methods which deal with multiple number of layers. So we all try to see which method is dealing with only homogeneous soil layer, homogeneous single soil layer, and which method is useful for determining the factor of safety when there are multiple number of layers. So this is what we will try to learn. So among the finite slopes, so the very first method is the pi is equals to 0 analysis. So when I say the angle of internal friction is 0, this inherently designates that the soil which you are dealing with is clayey soil. And you can see here, slopes in homogeneous clayey soil. Homogeneous clayey soil. So where the angle of internal friction is 0. So let us take, so this is an embankment. So the height of the embankment is h, and assume any trial slip circle. So AED. AED is called as a trial slip circle. So as you can see here, so this is perfect circle, circular in nature. So when you talk about the circle, there always exists the center of the circle. So O is the center of the circle. So O is the center of the circle. But so it is literally daunting task to determine the location of this trial circle. So in entire slope stability analysis, the biggest thing is what is the location of this circle or this slip circle. This is also called as slip circle or trial slip circle, whatever it is. Slip circle or trial slip circle. So what is the location of the trial slip circle determination is the biggest thing in slope stability analysis. It is not easy to determine. You may have to make numerous trials, which may be lakhs and crores of trials you may have to do often. Okay, so but it's not a one or two, it is thousands and lakhs. So this is where the software development of the software came in hand. So by which one can able to determine the most critical slip circle or the most critical circle corresponding to which the factor of safety is least. So when I say the factor of safety is say 1.2, so corresponding to this circle, the factor of safety means least 2 means, so possibly all along this slip circle there is a possibility of the slope failure, and remaining all factors are higher than this factor of safety. So they will not fail. They will not fail. For example, say, so this is another circle, so this is another circle, and this is another circle, so this is another circle. So you can draw any number of trial slip circles for a given slope, and corresponding to each trial slip circle, one can able to get a particular value of the factor of safety. So which may be higher than 1 or lesser than 1. So your aim is to determine corresponding to which slip circle your factor of safety is least, not a maximum, corresponding to which the factor of safety is least. Okay, so since in this case we do not know where is the location of the trial slip circle, so we are assuming some slip circle where AED is called as an arc of circle. AED is an arc of circle. So again, so among the 3 modes of the failure, that is slope failure, toe failure, and the base failure. So I am assuming that this slope is failing under the base failure condition. Okay, so here there are 2 parts again. So this circular, this is a base failure. So therefore the H is the height of the embankment, and the trial slip circle is passing even below the height of the embankment. So correspondingly, so we can divide the soil mass into 2 parts. That which is belongs to the embankment portion, that which is belongs to the horizontal portion. This may be natural ground or this may be the compacted ground. So the soil which may belong to the embankment portion, the soil which may belong to the natural ground circle. So in pi is equals 0 analysis, so it is normally assumed. Suppose say if W1 is the weight of the soil mass on one side of the center of the circle, that is O and E. So here B, C, D, E. So this is one weight of the soil mass, and A, B, E, A. This is another soil chunk. So therefore weight of A, B, E, A is W2, and weight of so D, C, B, E is W1. Now also try to understand. When I demarcated the weight of the soil of this element, that is B, C, D, E, and the weight of the element A, B, E, A. So one may act against the other. One may act against the other. Now, when you talk about the stability analysis, numerous methods have been evolved. But in each method, the fundamental distinction is somebody has considered only forces, somebody has considered only movements, and somebody has considered forces and the movements together. Forces and the movements together. For example, here, when I talk about, I can take the two kinds of the equilibrium. The first equilibrium is with respect to summation of only forces in the horizontal direction and summation of all the forces only in the vertical direction. And the second thing is summation of all the moments. So you can see I can take summation of all the moments about point O. About point O. So suppose if I take summation of all the moments about point O, I should multiply W2 into lever arm distance of L2 is equals to W1 multiplied by lever arm distance of L1. So by simplifying these equations, one can able to get the factor of safety equation. So this is the distinction between the force equilibrium and the moment equilibrium. But there are some methods which consider the force and the moment together. Force and the moment together. And some methods they consider exclusively only the force equilibrium. So this is up to you. And this is how different methods have been evaluated. So in this method, so again try to understand W1 and W2 are causing shear stress on the soil mass. And the CD, which is nothing but the shear strength developed all along the failure plane, which is in the direction opposite to the direction of the shear stress. Opposite to the direction of the shear stress. Since we are assuming the homogeneous soil, unit weight of the soil is gamma and the shear strength is nothing but Cu. When I say Cu, it is undrained cohesion. So it is undrained cohesion. So assumption, the undrained shear strength of the soil is constant with depth. So the undrained cohesion is constant all along the depth of the embankment. Choose a trial potential curve of sliding AED. This is initially we are choosing some trial slip surface. R is the radius of the trial potential curve and O is the center of the circle. So just understand that when I say R, that is the radius of the circle, O, that is the center of the circle, and theta is the angle made between OA and OD. So OA is the point which is connecting center of the circles to one end of the circle, and OD is center of the circle to the other end of the circle. So initially, I do not know what is the radius of the circle and where is the location of the center of the circle and what is the theta value. I do not know anything about all these slip circles. Okay. So in fact, one has to determine what would be the radius of the slip circle and where is the location of center of the slip circle. So these are all your aims of determining the factor during the determination of the factor of safety. So initially, I do not know anything. But there are the people who exclusively worked only on how to identify the center of the circle and how to determine only the radius of the circle. So there are some methods which exclusively allowed only for R determination and O determination. But there are some methods which doesn't talk about R, which doesn't talk about identification of O, but rather they will deal with only how to identify only the trial slip surface, that is A, E and C. So A, E and C. So there are all possible varieties of efforts have been made by the people. Okay, and still so efforts are being made how to control a slope failure. Although numerous efforts have been made, a lot has been understood about the slope stability. Still, we can see every now and then there is a failure of a hill slope, failure of an embankment, or the failure of so on and so forth. So let us try to interpret. So the total weight of the soil which is within the slip circle is W1 plus W2. W1 plus W2. So as we understand, so the weight is nothing but the total area multiplied by the density. So area of FCDEF. So this total area multiplied by the density. This is W1 and this is W2. So this is W2. So here they have considered the moment of the driving forces about O. moment of the driving force is about what. Now let's see. When I say the factor of safety, so this you need to understand. When I say the factor of safety, so how do you define the factor of safety here? So how do you define the factor of safety here?
Sir, CD upon the component of weight causing failure.
CD upon, okay, so maybe you can take the W1, W2.
Yes, sir.
So W, CD upon, so W1 plus W2. Okay, so as is rightly said, so CD upon W1 plus W2. Now, so let me give another picture. So I can term the CD as the shear strength. I can term CD as the development of the shear strength. And I can designate summation of W1, W2 as the shear stresses. The shear stresses. But when I talk about the factor of safety, here in this case, we need to understand whether you are going for force equilibrium or moment equilibrium. Force equilibrium or moment equilibrium. And when you talk about the force and the moments, then what you get is which one is the driving force and which one is the resisting force. So here then we need to redefine the factor of safety as the resisting divided by driving. Is this part is clear? The resisting divided by driving. When the resisting force is higher than the driving force, your slope is safe. So if not, then it is going to be the failure is imminent. The failure is imminent. So in this case, what you need to determine is you need to determine the total amount of the resistance force or the resisting moment, or total amount of driving force or the driving moment. So this is what you need to determine the factor of safety. Once you know this one, substitute everything into this form of the equation, simplify, then you are going to get the equation. Now here in this case, the CD is going to be acting as a resisting moment. Resisting moment. Now this is a force. CD is a force. So what would be the lever arm distance for this CD?
Radius.
Radius. So CD
R.
multiply R, correct. So if you multiply CD with R, then you are going to get the resisting moment.
Resisting moment.
Yeah. And if you look at carefully, since you are assuming this as a circular, so the R is remained same at any point all along the slip circle. Whatever the point you take it, so the R is remained same. Okay. So, but when you talk about the driving force, the driving force is caused by W1 and W2. W1 and W2. But let us look at, but the lever arm distances are different in case of the W1 and in case of the W2. So if you look at the driving moment, W1 multiplied by L1 and W2 multiplied by L2. But from the center line, so from the center line, the W1 is on one side and W2 is on the another side. So therefore, one will be positive direction, another will be negative direction. One will be positive direction, another will be negative direction. One may cause the driving, another may act as against the
And we
driving.
take W2 as the resisting force.
Pardon me?
He's asking if we can
Resisting force.
due to resisting force.
Oh, so you are saying, can I take W2 into L2 as a driving resisting force?
Yes, sir.
You can take it, but as long as you are not getting confused, there is no problem. Because if you remember, in entire slope stability analysis, since first class, we are saying that only weight is causing the shear stress. Okay, only weight is causing the shear stress. So if I take W2 into L2 as again resisting force, there may be a kind of a confusion. Okay, so as long as you are not getting confused, you are most welcome to take it. How does it matter? Whether you add W2 into L2 in resisting force, or you deduct from W1 minus W1, W1 into L1. So both should give the same value of the factor of safety. It is
Okay, sir.
immaterial. It is immaterial. Okay, so you are going to get same numerator, same denominator, wherever you take it. Okay, so this is the driving force, W1 into L1 minus W2 into L2, and try to calculate the resisting moment. So the resisting moment is whatever the cohesion that is going to develop all along the failure plane, that is CD, but CD is spread over a length of AED. CD is spread over a length of AED. So AED. So the cohesion is going to develop all along the length of the slip circle. It is not at one place. It is not at one place. And per unit length perpendicular to the monitor. Perpendicular to the monitor. So this entire thing will become the force component, and multiply this force component with the lever arm distance. So then what you are going to get is, so AED, so one can able to determine the arc length. Arc length, if I assume this is theta, if I assume this is a theta, so then I can able to determine the arc length. So if you substitute CD R, so the arc length is R theta. The arc length is R theta. So this is R multiplied by theta. So please correct me if I am saying something wrong. So R theta multiplied by CD into R. So this will become CD R square theta. So this is the resisting moment. So at equilibrium, the resisting moment must be equal to the driving moment. So I know the resisting moment, I know the driving moment. CD R square into theta is nothing but W1 L1 minus W2 L2. So you need to determine what would be the minimum cohesion required, that is CD is equals to W1 L1 minus W2 L2 by R square into theta. So this CD can be expressed in the form of, so the factor of safety, just recall the previous sum. So then factor of safety is nothing but the CU upon CD or CRC tau F by CD, whatever it is. You can define another way, either way, so it doesn't matter. So then this is what this one can able to determine the factor of safety. So if you define everything in factor of safety, then this will get, so Cu multiplied by W1 L1 minus W2 L2 by R square into theta. So this is based on the moment equilibrium. This is based on the moment equilibrium. So this is so need to make several number of trials for different circles, because from a single circle you will get only one factor of safety value. So Fs minimum obtained from one real circle is the factor of safety against. So then the CD by gamma H is stability number. I don't know how this just came. So CD is equals to this one. The critical height is possible when the factor of safety is 1. So I think up to this point is correct. So the Taylor further analyzed the same thing by substituting his number, that is stability number. This I think I will better skip it right now, because in between I'm missing some logic. So this is correct. Saturated clay, and this is for different slopes. So this is all right. This is all right. But where I'm missing the, so I'm missing somewhere some logic. So how to relate this equation with the stability number? So probably CD is the drained cohesion, sorry, drained cohesion. But no, this is undrained cohesion value, or CD you can say in terms of the shear strength. Then CD is equated to gamma H as per the stability number. So this is done by the Taylor. Taylor. So he has defined stability number, which is nothing but CD by gamma h. CD by gamma h. We can make another correlation between the Kalman's method and this method. In Kalman's method also we have a CD by gamma h. So which is again related to the beta and theta, beta and pi, beta and pi. Now here we can keep all right side one as a constant, that is weight and lever arm distances, then r and theta. R and,
Sir,
yeah,
CD is mobilized cohesion, na?
no, CD is not mobilized cohesion. CD is, we can say it is mobilized one, but CD is nothing but shear strength na. So shear strength can happen only at the failure.
Okay.
Okay, so CD can happen only at the failure. Suppose you let us look at, this is a resisting moment, which is nothing but the cohesion developed all along the trail slip circle. So it can go up to maximum value of the shear strength, because up to failure. Then if this is become the mobilized cohesion, there was no difference between shear stress and shear strength. That is not. Okay. This further took up by the Taylor. So he converted everything into his own, that stability number CD by gamma h. So then assuming the factor of safety of 1, so one can able to determine the critical height. So that is the Kalman's method, and this is how to determine the critical height in case of the saturated clays, in case of the saturated clays, or in case of the clayey soils where the angle of internal friction is 0. So here also, but we need to know what would be the value of theta and what would be the value of r and other things like W1, L1, W2, L2. And here also we know the slope angle, and the height. So as per our using the stability number, suppose as per this analogy, if you want to determine what would be the minimum or the critical height of the slope as per this theory, as per this equation, then we can relate this CD to the stability number. So that's how it has been arrived. So H critical is equal to Cu by gamma m. Then this will be further equivalent to W1 L1 minus W2 L2 by R square into theta. Now his further contribution includes, so this is how he has come up, the Taylor. So he has given different values of the stability number for different slope angles. But there are others also. So as for Taylor, up to beta of 53 degrees in 53, then there is no problem. But once it is exceeding 53, then there is another parameter that is coming into the picture, that is called as a D. So let us try to understand what is that D. So that D is the total depth of the soil from the top surface to the firm stratum. Okay, so in reference to this diagram, up to beta less than 53, the critical circle may be toe or slope or midpoint circle depending upon the depth of the function. So if beta is greater than 53, the critical circle is always toe circle. So this is what is the interpretation made by the Taylor, or several people in fact. So this is toe circle. Up to beta is 53. The trail slip circle always passes through the toe. Then if it is exceeding that one, then it could be anything. So when beta is greater than 53, it is toe circle. Less than this, then this is so any number. Anything can happen. Now when you analyze this kind of a slope, or you need to understand, so as I told in the just now, where the failure plane is starting and where the failure plane is initiating or ending or emerging. So we need to determine these two. So on the top of the embankment where the failure plane is going to be initiated, and on the natural ground surface where the failure plane is going to emerge. So if we can able to determine these two, then if at all if we are finding out that there is a possibility of the slope failure, then we can think of appropriate remedial action. So that intention, so they try to determine another two parameters that are called as the NH. So N multiplied by H. So this indicates at what distance from the toe the trial slip circle emerges. Okay, similarly, we cannot encounter a single variety of the. So I will stop it here only. So sorry, it's already 11 o'clock.